In this video, we will discuss the Z-score. In some cases, we are interested in how individual items in a data set fit into the collection. There are several common ways of creating such measures. Because they measure an item's position within the set, we call them measures of position. Each individual item in a sample can be assigned a Z-score, which is the first measure of position we consider. If X is a data item in a sample with mean X bar and standard deviation S, then the Z-score of X measures the number of standard deviations by which X differs from the mean. It is calculated Z equals X minus X bar divided by S. Note, Z will be positive if X is greater than X bar, but negative if X is less than X bar. By Chebyshev's theorem, at least 89% of the data in a set will lie within 3 standard deviations of the mean. So at least 89% of the data will have Z-scores between -3 and 3. Z-scores outside of this range are rare. For example, suppose for a given distribution, X bar is 340 and S is 22. Find the Z-scores to the nearest hundredth for these items in the distribution. X equals 349. Then Z equals 349 minus 340 over 22, or 9 over 22, which is about 41 100ths. If X equals 300, then Z is 300 minus 340 over 22, which is -40 over 22, or about -1.82, -1 and 82 100ths. And if X equals 382, then Z is 382 minus 340 over 22, which is 42 over 22, which is about 1 and 91 100ths. One common use of Z-scores is to compare relative positions of items in different distributions. For example, 2 friends in different history classes had midterms on the same day. One had a score of 86 with a class mean of 73 and standard deviation of 8. The other had a score of 78 with a class mean of 69 and standard deviation of 5. Which did relatively better? The first student has a Z-score of 1.625, while the second student has a Z-score of 1.8. So the second student, who received a 78, did better relatively. The higher Z-score means that her score positioned the student higher in their class.